All right. So could you please confirm if you can see my screen, Dr. Falcon?
Yes, everything is
Okay,
quite clear.
perfect. All right, perfect. All right. So welcome everybody and welcome to this presentation. So here's a quick overview of what we'll be covering today. So we'll start with an introduction to geothermal energy, followed by a brief look at its history. Then we will dive into the different type of geothermal plants, review some key statistics, and wrap up with a conclusion. After that, we'll have a quick exercise to test your understanding, of course, followed by a Q&A session where you can ask any questions you may have. So without further ado, let's get started with the introduction. All right, so the first question is, let's start by defining geothermal energy. So what is geothermal energy? Well, it is the heat that comes from Earth's core, which can be harnessed for various purposes. Geothermal energy is a renewable energy source that has been used for thousands of years, starting with ancient civilizations that used it for hot spring baths, all the way to modern power generation. So this energy is constantly being replenished by Earth, making it a reliable and sustainable renewable energy source for the future. So let's take a closer look on how geothermal heat is actually being generated within Earth. So the Earth's temperature increases with depth, reaching up to 4,200 degrees Celsius, which is around 7,600 degrees Fahrenheit, at the inner core. So this immense heat comes from the Earth's formation about 4.5 billion years ago, and from radioactive decay occurring deep within the planet. So heat travels upward through convection currents in the mantle, where the tectonic plates shift, such as mid-ocean ridges or volcanic regions, and this heat can escape to the surface. So the natural flow of the heat provides the energy that we can tap into for geothermal power. So this diagram here shows the plate tectonic process. So without going into deep detail, but let's just talk briefly about it, which is as it plays a critical role in geothermal energy. So the Earth crust is divided into tectonic plates that float on the semi-fluid mantle beneath. So in regions like the spreading centers, plates move apart, allowing magma to rise to the surface. In the subduction zones, one plate moves under another, pushing heat and magma toward the surface. So these tectonic movements generate significant amounts of heat, creating hotspots where geothermal energy can be harnessed. This heat is what powers the geothermal systems near the volcanic areas, mid-ocean ridges, or other tectonic boundaries. So how is actually the geothermal energy is being harnessed? Well, the heat from beneath Earth's surface is being captured, and it's used to generate electricity, heat buildings, and support industrial process. This energy is obtained by drilling wells into geothermal reservoirs located in areas with high tectonic activity or volcanic regions. So to harness the geothermal energy, the first step is the drilling of wells into the Earth's surface. So this diagram here illustrates a geothermal drilling process, which is similar to oil and gas drilling if you're familiar with that. So a rotary drill bit is being used to penetrate deep into the ground, reaching geothermal reservoirs that contain hot water or steam. The drill collar provides weight to help the drill bit cut through the rock, and a mud pump circulates drilling fluid to cool the bit and bring the cuttings to the surface. Once the well is drilled, a casing is inserted to stabilize the hole and ensure safe extraction of the geothermal fluids. This process allows us to tap to the Earth's heat and bring it to the surface for power generation. So let's explore some key characteristics of geothermal energy. Well, first, geothermal energy has low energy density in most areas, meaning it's spread out. However, in specific regions with a high geothermal gradient, such as the volcanic areas, for example, it becomes more concentrated. Next, geothermal energy has high energy potential in hotspots where it manifests as a steam or hot water, which can be used to generate electricity or heat. A significant advantage of geothermal energy is that it's very consistent. Unlike solar or wind energy, which can vary depending on the weather or time of day, the geothermal provides a stable, constant supply of energy year-round. This is very important to note. Finally, geothermal energy is unaffected by weather or climate, making it a reliable renewable energy source that can function in all weather conditions. So why is geothermal energy important now? Well, with the increasing demand for renewable energy sources to help reduce the greenhouse gas emissions and combat climate change, geothermal energy is now playing a crucial role in the global transition toward cleaner energy sources. Second, technological advances are making it easier to access deeper geothermal resources. This expansion of technology means that we can tap into geothermal energy in more locations worldwide, further boosting its potential as a reliable renewable energy source. All right, with that being said, let's now just dive deep into the history of geothermal energy. So, geothermal energy has been harnessed for thousands of years, primarily for simple purposes like thermal baths. Many ancient civilizations, including the Romans, Greeks, and the Chinese, used naturally occurring hot springs for bathing and healing. These early uses of geothermal energy laid the groundwork for how we understand and utilize the Earth's heat today, although the applications were much more basic than the power generation that we see in modern times. In the early 19th century, geothermal energy began to be used for industrial purposes. The first was in 1827, where the boron industry in Larderello in Italy actually started using geothermal heat to evaporate water and extract boron from volcanic ponds. So this marked one of the first industrial uses of geothermal energy. By 1837, Larderello expanded the use of geothermal energy for mechanical processes, further advancing its industrial applications. These early steps in Italy set the stage for how geothermal energy could be used on an industrial scale, beyond simple applications like heating and bathing. In 1904, the world saw the first geothermal power plant, built in Larderello, Italy. This plant generated electricity by harnessing geothermal steam. So this milestone marked the beginning of modern geothermal power, where geothermal energy was used not only for heating or industrial processes, but also for generating electricity on a large scale. So the success of this early plant paved the way for further development of geothermal energy around the world. In 1923, in California, USA, Grant and his family established the Geysers Development Company and built a 35 kilowatt geothermal power plant. This plant generated the first geothermal electricity in America, making a significant milestone for geothermal energy in the Western Hemisphere. By 1960, the geysers had grown into a large-scale geothermal power plant, becoming one of the largest geothermal fields in the world. This development highlights the expanding potential for geothermal energy outside of Europe. So after that, we have the global expansion where in 1928, Iceland began using geothermal energy for district heating, becoming a world leader in the direct use of geothermal heat for homes, schools, and other buildings. Earlier in 1919, Japan, and in 1921, California, they began exploring geothermal energy with the construction of the first power plants. And by the mid-20th century, other countries joined this, including New Zealand in 1958 and Mexico in 1959. So this growth shows the global potential and interest in geothermal energy from an early time. Now, moving on, let's talk about the different geothermal plant types. So the first type, there are three main types actually of geothermal energy power plants. The first type is called the dry steam plants. So these plants directly use steam from geothermal reservoirs to turn turbines and generate electricity. This is the simplest and oldest type of geothermal plant. Then we have the flash steam plants. In these plants, hot water from deep underground is brought to the surface and depressurized, causing it to flash into steam. This steam is then used to drive the turbines and produce electricity. Finally, we have the binary cycle plants, where these plants use moderately hot geothermal water to heat a secondary fluid with a low boiling point. So the secondary fluid vaporizes and drives the turbines, allowing electricity to be generated without direct contact between the geothermal water and the turbine. So let's start with dry steam plants, the simplest and oldest type of geothermal power plant. So these plants use natural underground steam directly from geothermal reservoirs. The steam is piped straight from the earth to a turbine which spins a generator to produce electricity. After passing through the turbine, the steam condenses into water and it's either released or re-injected back into the ground. This process allows for continuous energy production from natural steam sources. So this diagram shows the basic layout of a dry steam plant. Steam rises naturally from a production well deep underground and is piped directly to a turbine. As the steam flows through the turbine, it spins and generates electricity in the generating facility. After the steam is used, it passes through a condenser, where it cools and turns back into water. The cooled water is then re-injected into the ground through an injection well, maintaining the cycle and ensuring the reservoir is sustainable. Let's talk about the advantages of dry steam plants. So first of all, it is simple and efficient. So this technology has fewer components compared to other plant types, leading to easier maintenance and higher reliability. Moreover, no water separation is actually needed. So the dry steam plants directly use natural steam from the earth without needing to convert water into steam first. It is also an early proven technology where the dry steam plants represent the oldest geothermal technology first used in 1904 in Italy, demonstrating the decades of proven reliability and effectiveness. However, with every technology, there's always some challenges. The first challenges of dry steam plants is that there is limited availability. Why is that? It's because dry steam plants require rare geological conditions where naturally occurring steam is present. So this limits their geographic use to only specific regions because not every place have these conditions where occurring steam will be present. Moreover, there's also some environmental concerns because there's a potential release of small amounts of non-condensable gases, such as carbon dioxide and hydrogen sulfide from the steam, which could have some environmental impacts. So this is something to definitely take note of. Dry steam plants are primarily found in areas with natural dry steam reservoirs, as I said. Two of the most notable locations are the geysers in California, USA, which generates around 900 megawatts of power, making it one of the largest geothermal fields in the world. Then we have in Larderello in Italy, where the first geothermal plant was built. Now it generates around 800 megawatts of power. So these locations highlight the significant role dry steam plants play in global geothermal energy production. Now let's move on to the next type of plant, which is the flash steam plants. So the flash steam plants use high pressure hot water, which is above 180 degrees Celsius, from deep geothermal reservoirs. As the water is brought into the surface, the pressure decreases, causing some of the water to flash into steam. The steam is then directed to a turbine, which generates electricity. Any remaining water can be reflashed for more steam or re-injected back into the ground to sustain the reservoir, ensuring long-term operation. So the diagram here shows the operation of a flash steam plant. So hot water or maybe brine can be also used or extracted from a production well. As the pressure decreases, some of the water flashes into steam. This steam is then separated from the brine and directed to a turbine, which spins to generate electricity in the generating facility. Afterward, the steam is condensed back into water in the condenser, while any remaining brine is either reflashed for additional steam or re-injected into the injection well to maintain the geothermal reservoir. This cycle process allows for continuous power generation while keeping the geothermal reservoir sustainable. We also have double flash steam plants, where the previous one was just a single flash steam plant. So it's basically the same, where the main difference is that after the initial flashing, any remaining water is passed through a second flash chamber, where it's flashed again to generate more steam, and this is done to increase the overall efficiency. The non-condensable gases are compressed and removed, while the steam is condensed back into the condenser and re-injected through the re-injection well. So this two-stage process allows for more efficient extraction of energy from the geothermal fluid, maximizing the electricity generation. Don't worry if the diagram seems a bit confusing or complex. I'm just trying to provide this to give you an idea of how it's done in practice. All right, so let's look at the advantages of the flash steam plants. So the first advantage is that it's the most common geothermal plant. The flash steam plants are widely used due to the abundance of high temperature geothermal reservoirs, making them a common choice for geothermal energy production. Another advantage is that they're highly efficient, so these plants can generate more power by using multiple flash stages, such as or even triple flash systems to maximize energy extraction. Not only that, they're also scalable, which means that flash steam plants are sustainable for both medium and large scale power generation, making them flexible in terms of capacity. Now, let's discuss the challenges of flash steam plants. Well, first, it requires high temperature resources. So flash steam plants can only operate in regions with very high geothermal temperatures, typically above 180 degrees Celsius. So even though they are available, there's still some geographic availability limitations. Also, another issue is mineral scaling, where the process of flashing steam can lead to the buildup of minerals inside pipes, known as scaling. So this requires regular maintenance to ensure that the system runs efficiently and avoids any blockages. Flash steam plants are commonly found in high-temperature geothermal regions. Some notable regions include Iceland, Indonesia, and New Zealand. So these regions are ideal for flash steam plants due to their abundant high-temperature geothermal reservoirs. And the pictures here show some of the plants in these locations. Now let's talk about the final type, which is the binary cycle plants. So in these plants, a moderately hot geothermal water, so typically between 57 degrees Celsius to 180 degrees Celsius, is used to heat a secondary fluid that has a much lower boiling point. The geothermal water passes through a heat exchanger, transferring its heat to the secondary fluid, which is often isobutane or isopentane. So the secondary fluid vaporizes and drives a turbine, generating electricity. Afterwards, the geothermal water is then re-injected into the ground, while the secondary fluid is reused in a closed-loop system. So this diagram illustrates the process of a binary cycle power plant, where the hot water from the production well is circulated through a heat exchanger, where it transfers heat to a secondary working fluid. The secondary fluid vaporizes and drives a turbine, which is connected to an electric generator that produces electricity. The geothermal water, now cooled, is re-injected back into the ground through the injection well, while the working fluid is also cooled and reused in a closed-loop system. This design makes binary cycle plants ideal for moderate temperature geothermal resources using a highly efficient and environmentally friendly process. So let's review the key advantages of binary cycle plants. So first, it can use lower temperature resources. So unlike the other geothermal plants, binary cycle plants can generate electricity from low to moderate temperature geothermal sources. So this makes them actually more versatile. Moreover, there is no emissions involved because the geothermal water and the secondary fluid are kept in a closed loop system, meaning there is no emissions or direct environmental impacts. Lastly, it also has a wide application range, so the binary cycle plants can be used in areas that don't have extremely high temperatures, expanding the geographic potential for geothermal energy. As for their challenges, well, first, they have lower efficiency because binary cycle plants are generally less efficient, especially in higher temperature regions. This is because the flash system can extract more energy due to their high temperature. Moreover, it's also a complex system where the use of a secondary fluid and heat exchangers increases the complexity and the cost of the system. So this requires more maintenance and more infrastructure. Some of the binary cycle plant locations are in regions where they have lower geothermal temperature, such as Nevada, USA, Germany, and even Turkey. Now let's look at some statistics for geothermal power. This map shows the distribution of geothermal sources in Europe. The areas that are marked in red represent regions with high enthalpy geothermal resources suitable for power generation, like those found in Iceland and parts of Italy. Orange areas indicate high temperature basins that can be used for both power and district heating. Regions in yellow and light yellow show areas with medium to low temperature resources suitable for district heating or shallow geothermal systems. This distribution highlights the diversity of the geothermal resources across Europe, with regions like the Mediterranean and parts of Eastern Europe being rich in geothermal energy potential. This map instead shows the distribution of geothermal plants in Italy, particularly focusing on the region of Tuscany, where geothermal energy production is most prominent. The areas in red show the main geothermal plants in Tuscany producing significant amounts of geothermal electricity. For example, Pisa generates around 769 megawatts of power, while Grosseto produces around 17 megawatts. The map on the right shows the geothermal plant potential across Italy with different colors indicating varying temperatures at depth. So regions in green and yellow represent areas with high geothermal potential, which is ideal for power generation and district heating, while the others have lower potential. Italy has also been a leading country in geothermal energy, especially with its original history in Ladrello, which was the first geothermal power plant. We can also see here the geothermal energy production in Italy from 2000 to 2012, measured in gigawatt hours. We can see that the overall trend shows that geothermal energy production has been consistently high and it has been increasing over the years. How about the global stage? Well, this chart shows the geothermal power capacity and additions globally in 2021, highlighting the top 10 countries in terms of geothermal energy production. So the United States actually leads in geothermal capacity with over 2,500 megawatts of installed power, and they even added additional 25 megawatts in 2021. Indonesia and the Philippines follow, each with significant contributions, and Indonesia added an impressive 146 megawatt last year. Other countries such as Turkey, New Zealand, and Mexico also added capacity, reflecting a growing interest in geothermal power worldwide. Even Italy added 1 megawatt in 2021, maintaining its role as a key player in geothermal energy. Overall, the geothermal capacity continues to grow, with countries investing in expanding their renewable energy sources. This graph shows the growth of global geothermal electricity production and installed capacity from 1950 to 2015. The blue dots represent the installed capacity in megawatts, which has increased steadily over the decades, showing significant growth since the 1970s. The purple squares, on the other hand, represent the produced energy in gigawatt hour, which also demonstrate a sharp rise, particularly in the past few decades as the technology improved and more plants were built. By 2015, the world reached around 70,000 gigawatt hour of geothermal electricity production, with over 13,000 megawatts of installed capacity. This growth reflects the expanding role actually of geothermal energy in the global renewable energy landscape. How about the type of installed geothermal plants? Well, this pie chart shows the distribution of the different plants by capacity. Flash condensing plants make up the largest portion with 6,904 megawatts installed globally. So these plants are the most common due to their efficiency at high temperature. Dry steam plants account for 2,862 megawatt, a significant portion, particularly in locations with abundant natural steam like Italy and California. Binary plants contribute around 1,303 and are growing in use due to their ability to operate in lower temperature regions. Flash back pressure plants make the smallest share with 147 as they are less efficient compared to the other plants. So this distribution reflects that flash and dry steam technologies are actually dominating the market at the moment, but there's also binary plants being expanding in lower temperature areas. With that, let us conclude and talk and see what we've learned so far. So in conclusion, geothermal energy is a reliable renewable energy source. Unlike solar and wind energy, which are intermittent, geothermal energy provides a constant and reliable power source. It can operate 24/7, meaning that it's available in regions with geothermal potential. It also provides environmental benefits. So geothermal plants have a minimal carbon footprint and low environmental impact, especially with binary cycle plants, which operate with zero emissions. This makes geothermal a key player in reducing global reliance on fossil fuels and mitigating climate change issues such as global warming. There's also there's also technological innovation, where advances in drilling technologies and power plant designs help geothermal energy to be harnessed from a wider range of locations, including those with lower temperature resources. This means geothermal is growing more and more. There's also global expansion and future potential, where countries like Iceland, New Zealand, and United States have already demonstrated the vast potential of geothermal energy. So, with continued investments and innovations, geothermal energy can become a more prominent player in the global renewable energy transition.